Hello and welcome students. In previous lecture there was a discussion about two compartment open model. Now the very basis of having two compartment open model is that in one compartment we are presuming that the elimination of drug is a mono exponential process and it follows first order, but practically when we observe carefully, the elimination of drug follows two compartment model, which is a bi-exponential process and which is a sum of two different processes like the distribution process and the elimination process, and both follows first order reaction. In today's lecture, I am going to discuss about the method of residual. So this is nothing but a procedure where we can calculate various pharmacokinetic parameters after presuming two compartment open model study. So it says that the method of residual, which is also known as feathering, peeling or curve stripping, is a commonly employed technique for resolving a curve into various exponential terms. This method allows the separation of the mono-exponential constituents of a bi-exponential plot of plasma concentration against time, and therefore it is a useful procedure for fitting a curve to the experimental data of a drug when the drug does not clearly follow a one compartment model. Now please try to remember that the calculation of various pharmacokinetic parameter is very easy in case of one compartment model. But what if we are using a particular drug which is not following one compartment model, but instead it follows two compartment model? So by using this particular technique, that is method of residual, we can simplify the bi-exponential curve which we are getting after applying two compartment open model. We are converting that bi-exponential plot partly into mono exponential plot, and thus it would help us to calculate various pharmacokinetic parameters. For example, 100 mg of drug was administered by rapid intravenous injection to a healthy 70 kg adult male. Blood samples were taken periodically after the administration of drug, and the plasma fraction of each sample was assayed for drug. So a brief case study has been given that how can we utilize the method of residual in order to study the bi-exponential curve. How can we make it simple just like one exponential curve, and how can we calculate various pharmacokinetic parameters? So first we have to do a brief experiment, a small experiment, so in which a subject, whether it is human subject or the animal subject, so a subject has been given a fixed dose of drug, that is 100 milligram in this particular case, and periodically the samples have been collected and the plasma concentration of each sample has been determined. And when you plot a graph of blood plasma level, that is microgram per ml versus time, you will get this kind of graph where you can see that there is a curve and there is a straight line, right? So curve is about a bi-exponential behavior of the drug, right? Otherwise you would have got only a single line that represents mono exponential graph or mono exponential plot. Now when these data are plotted on semi-logarithmic paper, graph paper, a curved line is observed. A curved line relationship between the log of the plasma concentration and time indicates that the drug is distributed in more than one compartment. So what is the proof that the drug is following two compartment model? So in case of graph which we are plotting on semi logarithmic paper, so here we are getting a curve instead of a straight line. So the existence of curve indicates that the given drug is following two compartment model. From this data, a bi-exponential equation may be derived either by computer or by the method of residual. So this particular equation, that is a bi-exponential equation, we can derive after plotting a semi-log graph of drug plasma concentration versus time. The constant alpha and beta, or A and B, are rate constants for the distribution phase and elimination phase. So from the previous lecture you might have remembered that there are two different processes which are taking place simultaneously in case of two compartment open model. One is distribution phase and the other one is elimination phase. So here in this equation, constants like alpha and beta, or A and B, are representing distribution phase and elimination phase respectively. The constants capital A and capital B are intercepts on the y-axis for each exponential segment of the curve. So here you can see that when we backpolate or extrapolate this curve line, we are getting intercepts, and those intercepts are mentioned here. So these are capital A and capital B. As shown in the bi-exponential curve, the decline in the initial distribution phase is more rapid than the elimination phase. So you must be remember that this steep decline is because of drug being transferred to the tissue compartment or peripheral compartment from the plasma compartment or from the central compartment. The rapid distribution phase is confirmed with the constant being larger than the rate constant B. So in case of mathematical expression, you will see that the rate constant of distribution phase is much more higher than the rate constant of the elimination phase, because initially distribution phase is more predominant compared to the elimination phase. Therefore, at some later time, generally at a time following the attainment of distribution equilibrium, that is steady state distribution phase, the term A raised to minus alpha t will approach 0, while B raised to minus B t will still have a finite value. So the reason minus sign has been put here is that it indicates decrease in the plasma concentration or decrease in the drug concentration in tissue compartment. And when you put this particular equation into log form, you will get a simplified equation where log Cp, that is concentration of drug into central compartment, is equal to log B minus beta t by 2.3. So this is nothing but an equation like y is equal to mx plus c. So minus beta t divided by 2.3 is slope, and the minus sign indicates that the graph is giving us straight line with the negative slope. From equation, the rate constant can be obtained from the slope, that is minus b 2.3 of a straight line representing the terminal exponential phase. The t half, that is the concentration half, or the time taken to eliminate half of the concentration of drug for the elimination phase, or you can say the beta half-life, can be derived from the following relationship. So we can use this mathematical expression or the equation in order to understand the t half of elimination phase. A number of pharmacokinetic parameters may be derived by proper substitution of rate constant A and B. A is a rate constant for the distribution phase and B is the rate constant for the elimination phase, and intercepts A and B into following equation. So this particular equation you have to remember, and this particular equation you have to write in examination if this particular question has been asked. When an administered drug exhibits the characteristics of two compartment model, the difference between the distribution rate constant A and the slow post distribution elimination rate constant B plays a critical role. So we have to understand that if a drug is showing characteristics of two compartment open model, both these rate constants are playing very critical role. The greater the difference between the A and B, the greater is the need to apply two compartment model. So suppose we are in a puzzle that whether we should apply two compartment model or one compartment model. So we can cross check this thing by finding the values of constant A and B. If the difference between the both constants are very wide, then definitely the drug is following two compartment model. Failure to do so will result in false clinical prediction. So this would be very critical for conducting any clinical trials. On the other hand, if this difference is small, it will not cause any significant difference in the clinical predictions regardless of the model chosen to describe the pharmacokinetics of a drug, then it may be prudent to follow the principle of parsimony when selecting the compartment model by choosing the simpler or the two available models. For example, one compartment versus two. So please remember this particular point. Next is apparent volume of distribution. So the apparent volume of distribution Vd is a useful parameter that relates plasma concentration to the amount of drug in the body. For drug with larger extravascular distribution, the apparent volume of distribution is generally large. Conversely, the polar drugs with low lipid solubility, the apparent volume of distribution, that is Vd, is generally small. So what you have to remember from this particular point, that drug which is hydrophilic in nature, which is highly water soluble, are having higher apparent volume of distribution, and drugs which are more lipophilic in nature, having more lipid solubility, are having less volume of distribution, apparent volume of distribution. Drug with high peripheral tissue binding also contribute to a large apparent volume distribution. So these things you have to remember. Then the volume of the central compartment. So this is a proportionality constant that relates the amount of mass of drug and the plasma concentration immediately, that is at 0 time following the administration of a drug. So the ideal time to calculate the volume of central compartment is to find out drug concentration in blood immediately after the administration. The volume of the central compartment is useful for determining the drug concentration directly after an IV injection into the body. Here you can see an equation to calculate volume of central compartment. In clinical pharmacy, this volume is also referred to as VI, or the initial volume of distribution, as the drug distributes within the plasma and other accessible body fluids. Next is apparent volume of distribution at steady state. So this is proportionality constant that relates the plasma concentration of the amount of drug remaining in the body at a time following the attainment of practical steady state, that is reached at a time greater by at least 4 elimination half-lives of the drug. So this is a situation where there is a steady state condition where the amount of drug which is going from the central compartment to the tissue compartment and from tissue compartment to the central compartment is almost identical. At steady state condition, the rate of drug entry into the tissue compartment from the central compartment is equal to the rate of drug exit from the tissue compartment into the central compartment. And a particular mathematical equation has been given to calculate the apparent volume of distribution at steady state. Next is extrapolated volume of distribution. So this is also a one type of volume of distribution, and a specific mathematical equation has been given where capital B is the y-intercept obtained by extrapolation of the B phase of the plasma level curve to the y-axis. So all these parameters you can calculate once you plot that bi-exponential curve of drug plasma concentration versus time. And the last one is volume of distribution by area. So the volume of distribution by area, that is Vd, also known as Vdb, is obtained through calculations similar to those used to find apparent volume of distribution or the volume of central compartment, except that the rate constant, that is small b, is used instead of the overall elimination rate constant k. This volume represents a proportionality factor between the plasma concentrations and amount of drug in body during the terminal or B phase of disposition. So the mathematical equation to calculate volume of distribution by area is given. So you have to remember all these equations from the exam point of view. So dear students, that was all about the method of residual. I know these topics are slightly complicated and it will be difficult to understand because this is entirely a hypothetical study, but repeatedly you have to read all these things and you have to try to imagine in your mind that how things are working, because in practical we are not able to see this kind of things happening because it is a hypothetical scenario. So please go through this video and let me know if you have any query or question. Thank you very much. Have a good day.